Yeah, she will wear it. Okay. So thank you all for coming in for this very special set of lectures. Um, the Natural Sciences faculty is really delighted to be part of this set of lectures with the School of Mathematics. So I want to thank Mahan and everybody behind the scenes who have been working to get these set of lectures for this year's Fields Medal. I would also like to thank all the speakers coming in here, traveling to Mumbai for coming in for this special colloquia. Um, would like to mention one thing. I'm Jyotishman. I actually host the NSF colloquia for those who um, are coming for the first time in this lecture series. We are very happy that we are tied up with this particular occasion. Um, and I look forward to more interactions with the School of Mathematics through our NSF Colloquium series. This is something that we would like to build up on a larger time scale. So thank you. Um, I will not take much time. I'll just say that uh, because of the way TIFR has been constructed by our founding director, it's always nice to have all the scientists within the community at least sit together once and listen to fantastic colloquia. So this is one such opportunity. I hope we will have many more, and there'll be stronger interactions within us. So with that, with those words, I would like to let Mahan take over the proceedings. So
Yeah, thanks, Jyotishman. And yeah, so firstly, thanks to the NSF and the Jyotishman for ensuring that, I mean, this was a bit of a logistic nightmare, which was handled very expeditiously by all concerned, myself excluded. So the thing is, today's thing is essentially we sort of borrowed this slot and from the NSF thing from 4 to 5, which is the standard colloquium slot for NSF on Wednesdays. And so they gave it to us and we extended it half an hour this way, half an hour that way. So today's thing is, you'll see a little bit of an asymmetry between today's talks and tomorrow's talks. Part of it is to ensure some logistic thing and part of it was to sort of ensure that we have resource persons. So today, yeah, it's my real pleasure to introduce both Professor Shobha Madan and Mahesh Kakde. One of the reasons why they are the speakers in the Maryna Viazovska celebration of her work is a while back, I mean, 2019 or so. Some of you might remember Abhinav Kumar's visit to TIFR. Around that time or a little before, there was a 1-week program and Viazovska's work had just come out and there were various angles to it. I mean, and at least 2 angles we hope will be explicated here. So there were people from harmonic analysis, people from number theory. There's a bit of linear programming also involved. I don't think that's going to be covered here. Anyway, so these people had been part of that thing 3 years back before Viazovska had become the, well, sort of celebrity. So this was sort of purely on, I mean, so people have been talking about this for a while in India. And so it's, yeah, great pleasure to first have Professor Shobha Madan talking about the harmonic analysis angle to her work. Just one thing, if anybody has any questions, please raise your hand and we'll reach this or some other mic here to you. Okay. All right. Over to you.
Green light. Okay, I'm very happy to be here in TIFR. I have to thank Mahan for inviting me. I know very little about this whole theorem, major theorem that Maryna Viazovska and later on, along with collaborators. But I do some harmonic analysis and it caught my attention because of very beautiful use of a theorem that I like very much. So that's how I got into reading a little bit. So the first slide here comes from 2016, and I've stated the date here, March 14th, 2016 is when Maryna Viazovska uploaded her paper on arXiv. And I mentioned the date, which was called the sphere packing problem in dimension 8. We will talk about the sphere packing problem to begin with. And exactly a week later, another paper was uploaded by her and several of her collaborators, where they solved the sphere packing problem in dimension 24. So I want to sort of talk about it. Why 8? I mean, 8 and 24 doesn't mean you know anything about anything in between, but 8 and 24 were somewhat special, and that will show up by yet another subject called linear programming. So this is when she got the breakthrough prize thereabouts at that time. So this is a sphere packing problem. At the moment, I'm stating it slightly loosely for you to understand what I'm talking about. You take a set of congruent balls. Congruent means same radius wherever they are centered in the Euclidean space Rn, and then so anything can be a packing. Like this hall is not packed, but it is a packing with gaps, lots of gaps. So congruent balls with disjoint interiors. That's what a packing is. And the question is, what is the densest packing? We are talking here about spheres. So anytime you put spheres together, there'll be gaps. However close you put them, as long as they are disjoint interiors, there will be gaps. So you want to actually measure the proportion of volume occupied by these. I say simply here in a large box, that means in an asymptotic sense. You take a large box or a large sphere, and then you look at these spheres that are in there, and you look at the volume being occupied by them in proportion to the total volume. That's called a sphere packing. So just to get started in dimension 1, it is trivial because you can just place intervals. I've not mentioned the length of the interval or radius of the spheres, it doesn't matter. But in dimension 1, there is nothing to prove. You just put interval, there are no gaps, and that would be the densest packing. And if you have intervals of unit radius, I'll call it radius because that's the ball. So whether you take unit radius or whether you take any r, it's the same thing, same result, same packing. It doesn't matter. In dimension 2, it's not that trivial. This is sort of what I call the best packing. I should have got other pictures, but I'm clumsy about getting all kinds of pictures downloaded. But this particular packing is each sphere has 6 neighbors set in a hexagonal manner. Their centers are sitting in a hexagon. And that this is the kind of densest packing you will have requires an idea. And it was proved in, so Lagrange in 1773. So when you talk about packings, the centers of the spheres are sitting in with some pattern. That's all that matters, the radius. So these are called lattice packing. There is a lattice, and its lattice points are the centers. So the packings need not be sitting on a lattice. It could be very arbitrary sets. But if you try to answer this question by saying that the set of packings I'm going to look at are only lattice packings, then Lagrange was able to prove that the hexagonal packing, whose picture I just showed, is going to be the best packing. Maximum volume occupied is what is being said. And the packing density, which I shall define precisely, will be pi by square root of 12. So among lattice packings, the densest packing is hexagonal with packing density, which is given in this. So there is a little history here that in 1890, Axel Thue published a proof that the same density is optimal among all packings, not necessarily lattice packings. So that's a much harder problem. And his proof perhaps was somewhat incomplete. And although the theorem is ascribed to Thu, in 1940, Toth gave the first complete proof of the general case involving all arrangements. This already takes a little bit of work. It's not as obvious as one dimension. And in dimension 3, this is another story. The story is that Lord Rayleigh, he wanted to know how best to stack cannonballs on his ship's deck. He was an explorer, among being various other things. How best to stack the cannonballs on his ship's deck to maximize the number of cannonballs. Actually, this is the same thing that fruit sellers do with oranges. They pack in a carton, they don't just randomly put, they put it in a certain fashion. And they seem to know what is the best packing to get maximum number of oranges inside a box. So he asked a mathematician friend of his, who then posed the problem to Kepler, and he conjectured that if you're looking at all packings, not necessarily even this thing, it was merely a conjecture, then there are these face-centered cubic and hexagonal closed packing. This includes the fruit sellers packing, certainly, but there are two. And the way this works is, I have a very bad three-dimensional image. This thing is that you layer it, you put a set of cannonballs in the tightest packing as per 2 dimensions. And then there is a natural way of putting the next layer and then the next layer. And there are more than one ways, precisely 2 ways of doing this. And those are the 2 that are going to have the same density and the densest one. A good way to understand this, I thought, was a video in the number file, which is called The Best Way to Pack Spheres. It's fun to watch that. So, but this remained a conjecture and is called the Kepler conjecture. It is, in fact, formed a part of the 18th problem in Hilbert's list. So it was of some interest too. And this problem is, so Gauss proved that the Kepler conjecture is true if spheres have to be arranged in a regular lattice. Again, the same special case of this thing. And Thomas Hales has proved this. There's a little story here because I write the dates as 1998 to 2014. What does that mean? So 1998 is when Hales submitted his paper to Annals of Mathematics. The story is that there were 12 referees. This particular proof involves a huge amount of computer calculations. And the referees just got completely tired. Some of them even left. And in the end, they declared that the proof was 99% verified. And they do believe that the result is correct because the analysis is correct. And it was published. It was published in 2003 or something like that. However, Hales then decided to settle this issue, and he got some 24 people to do a formal proof checking, again using the computer. It took about 12 or 13 years to finish that. It is now considered proved. And so that project finished in 2014, and it is published in 2016 or 17. So Kepler's conjecture is now proved. Now, if you expect me to go to dimension 4, I won't. One cannot go on like this for 45 minutes. Not because it's boring, because nothing is known. You know, dimension 4, there is absolutely not only not known, there is not even a guess. Every dimension seems to have a different circle. So let me be a little more definite. Let me define what is density formally defined mathematically. So I call P a union of congruent balls with disjoint interiors in Rn. Then the upper density of P, I have exactly defined it, that the volume of the balls, volume of P intersection, a ball of large radius R, divided by the volume of this big ball. If I take the limb soup, then it is called the density of that part, that packing. And then if I take the supremum over all packings, that's called the density in Rn, of sphere packing in Rn. So that would be the supremum of all upper densities of all sphere packings. That is the density definition. So as I said, delta 1 is known, delta 2 is known, delta 3 is known, and now delta 8 and delta 24 are known. And it doesn't mean the fact that we know delta 8, it doesn't mean that we know 4, 5, 6, 7. Nothing is known there. This is a statement because for for 3 dimension, you're building it layer by layer and it works. It doesn't work like that in other dimensions, layer by layer building up. And dimension 8 here is the special one that led to dimension 24. And there is another reason. Okay,
that there will always be a unique densest packing?
no, because already in dimension 3 there are, no, that's not known. We don't even know whether it will be necessarily a lattice packing. It could be very wild. So this picture, however, is what comes from linear programming methods. I don't know anything about that, how this is achieved. But there are 3 lines here. The lowest red line is what is the lower bound of the ball. This is 2 to the power minus n for every. So it's a lower bound. It's not necessarily the lower bound. And people, including Venkatesh, is been trying to improve those bounds, but that's not satisfactory. That doesn't concern us now. The blue line is what they have plotted as the densities of all known packings in each dimension. Known is usually by existence of certain lattices. And the green line is what they, from linear programming methods, get the linear programming upper bound. This is not the best picture to have because the things are small here, but there are 2 points. One corresponds to n equal to 8 and the other corresponds to n equal to 24, where this lattice packing seems to just touch the upper bound given. The known packing reaches up to the upper bound and we don't know whether it is exactly that. So those 2, dimension 8 and 24, are something that catches your attention. And these.
Can I ask a quick question? Sorry. These numbers in the blue, right?
Yeah.
How did they compute that? The best packing in like dimension 18, 19, 20. How did they compute that?
No, they're not talking about the best packing. They're known packings.
They're known packings. Okay.
So the blue one are all known packings.
Okay.
So among the known packings,
whether best or not is not known.
No, not
okay.
at all.
So that's your upper
bound. Upper bound. So whether they are the best, we don't know.
Okay.
So what we, yeah.
In this case, what does the lower bound even mean? You already know packing with a higher density than that. Isn't that the lower bound?
No, that's an academic kind of question. It's the kind of doubling argument. You have a packing which is optimal that you can't put in any more spheres. Then you take this packing, you double the radius, right? If you can't put any more than this doubled spheres, their union will contain your ball of radius R, capital R, large ball. And so if you take a ball of twice the volume, it is 2 to the power n times the previous one. That's all. It's a very bad lower bound.
The lower bound works in any dimension, whereas this blue stops wherever it stops.
Yeah.
I mean, the blue is consistently higher than the red. You might as well abandon the red.
Yeah. But there are several questions. I told you I can't get the best picture. There's a very nice bigger size picture without the blue, without the red. So, okay.
What about 60 to like a slightly.
The blue is something computational, right? So it has been done up to some number. It's not for all n.
No, 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 up to 36.
Yeah. So
They
whereas
have
this- whereas
calculated.
the red one is for all n. So it's
Yeah, the red one is for all n. That's the only statement being made. And the blue one, they have computed up to dimension 36. It's big computations.
So dimension 16 looks like a slightly hopeful situation in that picture.
The 16 shows a little bit of a bump, and expectation certainly is something about 16, but it's far short of the bound as multiples of 8, but we have no idea about, no more about it. Okay, so the ingredients in this circle of ideas is linear programming bounds, which I've talked about. Surprisingly, some quite simple in a sense, but somewhat interesting, something called Poisson summation formula in harmonic analysis, which I will state and prove and tell you how it is used. In dimension 8, I'm not going to talk about 24. I'm going to only talk about dimension 8 to some extent. The lattice E8, I'm going to use some facts about the lattice E8 without knowing what the lattice E8 is essentially. It is a vast lattice of great interest in lots of other subjects. In fact, physicists think that it will provide the theory of everything. So, as they say. And then the crucial and completely surprising is the use of modular forms in the construction of some functions which the Poisson summation formula's application demands. Okay, so let's get down to some Fourier transforms. So just the definition. I bet everybody knows the definition. I just usually state it to tell you where the factor 2 pi occurs. It's defined with exponential minus 2 pi I x dot xi. You don't put 2 pi, it appears somewhere else. So that's going. And one of the things that's going to come up will be some eigenfunctions. And the Gaussian is an eigenfunction of the Fourier transform, which I suppose in some complex analysis class everybody has worked out by contour integration. I have written here F belonging to L1 Rn, that is the Lebesgue space L1, but I'm not going to need this large space because there are lots of very complicated results in harmonic analysis for LP spaces, but a much smaller class. And that smaller class is what I will call nice functions. By nice is that they have such nice properties that you have no hesitation in interchanging integrals or looking at the rate of convergence, uniform, etc. And this is a space called the Schwarz class. Schwarz class is a set of functions which is C infinity, and the functions in this class decay faster than any polynomial. So e to the power minus x square is an example, but so do all the derivatives. Because you take derivatives of e to the minus x square, you keep picking up some polynomials. So it has a what is called a rapid decay, that means faster than any polynomial. And this is the Schwarz space. It has the advantage, which none of the other spaces do, is that the Schwarz space, the Fourier transform maps the Schwarz space to itself. It's an isomorphism. So you can go back and forth, which is something you can't do for the Fourier transform in general, because there is no other space that has these properties. So when I say now onwards let f be a function, I mean it's a nice function, so that I will not have any convergence issues, etc. We'll also need Fourier series. So once again, I just write down the. Now, here I say that f has a Fourier series. Every function, even in larger spaces like L1, has Fourier coefficients, but may not have a Fourier series. There may be no convergence. But then f by here now onwards will mean nice. In fact, has a Fourier series expansion, and then the convergence is uniform, etc. Everything is nice, with coefficients as defined above. So this is the famous Poisson summation formula. It basically says that if f is a Schwarz-Class function, then the summation over k, f evaluated at k in, right now I'm talking only about R, is the same as the sum of the Fourier transform evaluated at the integers. In itself, it appears very strange. Why, these, although there is a lattice there, but it looks much better if I look at it as a function. Notice that if in the statement, this is true for all Schwarz-Class functions, then given a function, it is true for its translate. That's again a Schwarz-Class function, right? So I am writing now below the one periodic function. I'm basically just taking the translate and putting down the left-hand side of the thing that I require to prove. And then when I evaluate it at 0, I will get that result. Conversely, if I have for f, then it is true for the translate. So they are equivalent. And proof is simply this, that f sharp, which is a periodization of f, is again going to be a nice function. It will have a Fourier series. And I simply, what the Fourier series is, I have to calculate. That means its Fourier coefficients will be f sharp hat at j, f sharp hat, whatever they are. But then if I integrate 0, 1 summation k belonging to z, I basically get the integral over the whole real line, because 2 pi I jx is also unperiodic. So you just push that inside. So f sharp hat is the same as f hat. So those are the coefficients. That's just an observation, if you like. So that's still evaluate. There's an L missing there at x equal to 0. And the same argument, if you carry out for a discrete lattice in Rn, it will bring in the Jacobian of the way the lattice is defined. And that is the volume of Rn by lambda, where Rn by lambda is to be identified with the fundamental cell of the lattice. So this is the more general situation where you have a lattice. And you can see that there is a lattice coming into the picture because there will be some packing, etc., over on lattice points. All right. So Cohn and Henrik Cohn and Elkies, who produced that graph of the packings, they proved a very interesting theorem. And this theorem states that if in Rn, now we're not talking about packing or anything at the moment, in Rn, independent of everything, there is a Schwarz-Class function which satisfies these properties. Before I state these properties, I should state that the thing about functions and Fourier transform is that you can't control both of them. Essentially, this goes back to Heisenberg uncertainty principle. If you want some control on f, you lose control on f hat, and the other way around. But this is a theorem that is going to require some control on both. So if you have a function which is Schwarz-Class, and first it satisfies that the value at 0 for both f and f hat is 1, fx is less than equal to 0 for all x greater than r for some r. I won't specify the r at the moment. And f hat xi is always positive. Then the sphere packing density is bounded above by the volume of balls of radius r by 2. That same r that is occurring over there. So this is, that means you are going to look for functions. This is a nice upper bound, and in some cases it is actually achieved by a packing. But out of the blue, from somewhere, if you can produce functions like this, then you have this nice upper bound on the density. And effectively, these are the functions that came to be called magic functions. So they were looking for that. This will be magical if you find them. And then the magic function term can be shifted to another set of functions that because you can conclude a lot. Okay, and then the sphere packing density, which means any packing that you take, not less, will have density less than this volume of Br by 2. Now, when I want to prove, since we are talking about any packing here, that's hard to tackle. One thing that we will do is to that it will be enough for us to look at periodic packings. Periodic packings are, there is a lattice behind it and then some translates of the lattice that you take. Then it just means that that's a periodic packing. Why? Because you can, when you look, because the density of the general case can be approximated by densities of the periodic case. You take large boxes of the arbitrary packing and you periodize, then you get a periodic packing. The larger box you take will get the density even closer. So we'll look at only the periodic case. So I'm going to prove this theorem. So we take a periodic packing and we are taking spheres of radius r by 2 centered at the translates of a lattice by some vectors t1 to tn, capital N, where r here I am going to choose. R is the minimal distance between points of this translated packing. Minimal distance is r, so when you put balls of radius r by 2 on the vertices of this set, they will not overlap. That much you need. So where r is the minimal distance, then the density is given by, this requires a little bit of work, that n times the volume of Br by 2 divided by the volume of the fundamental cell. Because in the fundamental cell at the vertices, if you put the part that comes into the fundamental cell, from each vertex will add up to a ball. So that's how the n will come. Is that part okay, or I need to draw a picture in 2 dimensions? So in this case, we will simply prove that the volume Rn by lambda is greater than capital N and will be done. So we use Poisson summation formula for that. So here the summation, we need to sum over each of the translates and take the sum x in lambda ftj minus tk plus x. Now I'm using x for points in the grid. This, if you expand it out, use Poisson summation formula, will shift to that right hand side. By combining terms, you will get a modulus of e to the power 2 pi I by tj mod square. And the sum there is over the dual lattice lambda star. Now, here notice the hypothesis. If I look at the left hand side, except for the term that is going to correspond to the point 0, everything else is greater than r, and therefore f is negative by our hypothesis. So the left side is less than nf0. You're just subtracting something from there all the time. And the right hand side, because f is positive, we're just dropping a few terms, many terms, and you'll get that the right hand side is greater than n square, because that last factor will give you n square. Except for 0, we are rejecting everything else, and then we are done. Yeah. So the volume then will be greater than capital N. Now, given the conditions in the theorem, we can assume that f itself is radial, because you take f and you take the average around the spheres. The theorem doesn't change. The conditions given are all nice and radial. So that's a big advantage to begin with. After all, then it is a function of one variable on Rn. It's a function on Rn, but as a function you can think. So we can assume that the function f in this theorem is a radial function, and for a radial function, f hat is f, because when you take the inverse Fourier transform, there's a minus sign that appears. Now with this being a radial function, that minus will collapse. So that means if I put f plus as f plus f hat by 2 and f minus as f minus f hat by 2, then f plus and f minus are eigenfunctions with eigenvalue +1 and -1. So radial function and eigenfunctions, two of the Fourier transform. And this is where the Gaussian is going to play a part. That is, out of the Gaussian, we would like to generate eigenfunctions. Yogesh, you are sleeping. No, you are welcome to sleep, but in a later row, not right in the first. I have this rule in the first few rows. It's infectious. Sorry, I can do this. He was my student once upon a time. Okay, I am now going to mention only this fantastic lattice E8. Just for completeness, I give the definition. I'm not capable of, it's great fun to see pictures of the E8 lattice and all kinds of things. They look like very artistic things, but I'm only going to need these 3 or 4 facts. And one is that it is its own dual. The volume of the fundamental cell is 1. The minimal vector in E8 has length square root of 2. So if the minimal this thing, then I will use the packing will use balls of radius 1 by square root of 2, half of that. And the sphere packing then has the density volume of B8 by 1 by square root 2, which is precisely the volume calculated as pi 4 by 4 factorial into 2 to the power 4, the ball in radius. And the vector lengths, now I'm worried only about the lengths because I have a radial function to deal with, are of the form square root of 2k. So I don't need anything more. So now the thing is the magic function we want to look, we have got extra properties now. We need to find the magic functions, we need to find a radial Schwartz class function F1R8 satisfying the first 2 properties mentioned in Cohn-Elkies theorem, with now R being square root of 2, particular R. I need to find F with this property 1 for R equal to square root of 2, F hat xi positive. And the third one follows from 1 and 2 for the following reason, which is given here once again by Poisson summation formula, which is in the last line first. I'll say something about the order. By Poisson summation formula, what we did applied in this case is we wrote the inequality by just simply rejecting the other terms other than 0. Because on one side they were negative, on the other side F was always positive. But this is this inequality here because we have put the condition that F0 is equal to F hat 0. So equality will have to hold. The only way equality can hold, because we kept one term and rejected the rest, is if the rest of the terms should be 0. And that means that F of square root of 2k would be the zeros of both F and F hat. And we don't want, we have F0 is going to be less than 0 beyond R, which is square root of 2. So we don't want beyond that the sign to change. So these zeros cannot have order 1 because then it will cross. So these have to have order 2 at least. And the other side F is positive. So these zeros again would have to be order 2. There is a little catch here, is that this is true only for square root of 2k. For k equal to 2 onwards, because at 1 we want F to cross the axis, which means the 0 should be of order 1, and we don't want the 0 to be at 0 because the values there are given to be 1. And that is a slightly somewhat problematic situation, but that is to be dealt with later. So at this point, having analyzed all this, Elkies, they were searching for these magic functions. This is 2003 onwards. At that time, Maryna Viazovska was probably a school student. So they were searching in all kinds of domains of mathematics as to where will these functions come from? Where do they come from? So they worked very hard and they convened a conference or two to disseminate the problem in the hope that somebody will say that such functions can be found. But they didn't know which areas of mathematics to search in. And then it is said that Viazovska really pulled a Ramanujan using modular forms. So okay. So anyway, we try to see how to reach up to that. So eigenfunctions of Fourier transform, there are ways and ways of generating those. She uses this transformation, a Laplace transformation kind of thing, knowing that Gaussian is an eigenfunction and to try and generate from there. And this is the way. So once again, you take a function h, which is nice, and then you are taking a sort of a continuous linear object with of e to the power minus t by t mod x square multiplied by ht. Those are the so-called coefficients at t, if you want to call that. And then you say what you'll get. You compute g hat by a straightforward computation. And then you notice if at all g has to be an eigenfunction, then you look for the condition that will make that happen. And then h of 1 by t should be some epsilon lambda or something like that multiplied by t to the power 2 minus n by 2 ht. Then g hat g will be an eigenfunction. So if you write ht, you go up to the complex plane as phi of it, then the condition looks like phi of minus 1 by z, z to the power k phi z, never mind the k being whatever it is. It immediately suggests some connection with modular forms. So that is what the definition sort of looks like. So now coming to dimension 8. So if we come to dimension 8 and try to look for the magic functions, because 8 is already indicated as a special dimension, the zeros part of it, she tries to accommodate by putting the sine square pi x square by 2. It has the correct order of zeros for the square x equal to square root of 2k. In fact, it has zeros of order 2 even at k equal to 1, but we don't want that. That factor we are putting in, but it has an extra order of 0 at 1. And at 0, in fact, it has a 0 of order 4. So this has to be compensated by the other factor, which is coming from the transform, the integral from 0 to infinity, which is an issue that Mahesh may or may not deal with. Okay. So Viazovska then was able to find a function. Let me go back to this slide. Of using modular forms, a very explicit formula for a function which is not itself a modular form, but it is constructed out of modular forms in dimension 8. So it's very complicated. I have no knowledge about this. And she will give you a function which will have these properties. So that is basically as far as I will go in the use of Fourier analysis.
सीधा करना, हाँ सीधा, नहीं तो टिल्ट हो गए तो मुश्किल हो जाएगा. मैं देखता हूँ.
Sorry about that. Oh, that's okay. Anyway, I'm about to end. So what I'd like to say is that this technique that she uses to generate eigenfunctions, that Laplace transform technique, thereafter of course, gave the similar result, similar construction, not similar, but much more complicated construction for dimension 24. But it seems to give much more by using the same technique. So it's a technique which is very powerful to produce results. This is now dimension 8 business is over. I've only stated one result, which I find very surprising. Using the integral transform technique, a collaborator, Radchenko and Viazovska, constructed an interpolation formula for even Schwartz function. This is, what does this say? For even Schwartz functions, independent of anything, you can produce a sequence of functions an in R. This is talking in R, such that every even Schwartz function f can be reconstructed using the interpolating functions from the values of f at square root of n and the values of f hat at square root of n. You're using very little. If you talk about sampling, then you are sampling the function and its Fourier transform only at the point square root of n and getting the full function f, provided you reconstruct it using an and an hat. It's not an and bn either. It's you construct one function and take its Fourier transform, and from a very sparse set, you can reconstruct f. This is what something that happens in the famous Shannon sampling theorem. You have this function sinc n, which are the interpolating functions that do this. And there are more results like this, even in Rn. So that's the excitement. Because a harmonic analyst will say, now what is square root of n doing here? These are surprising results. So I will sort of stop here.
Questions? Yeah.
Thanks for a really nice lecture, and I'm sorry if this question is not really well posed, but the results you have shown so far are like for 3 Euclidean dimensions, right?
Yes, yes.
As in, we think of as
1, 2, 3, and 8. Yeah.
Sure. What if does the picture change radically if you're thinking about like Minkowski space or something? Because I'm a physicist, so I
Remind me, what do you mean by Minkowski?
if in the metric one of the signatures is time-like, like has -1 or.
Well, I don't think there has been any consideration of those kind of things, but probably not.
Questions or comments? Mahan, you have something?
No, I was just wanting to ask SM to move to the references so that people.
Oh, I forgot. Yeah. My only references is what I'm capable of. I'm not. So Henry Cohn had a paper already in 2016 where he describes a conceptual breakthrough in sphere packing. This is an interesting paper that people can. It's not even a paper. It's just basically an article he wrote to prepare you to read Viazovska's paper. So it describes things in detail. So it's very fruitful to read as much as you can. And Maryna's paper, the first part is readable. But the second part, I have checked line by line that some function is an eigenfunction, but I don't know where the functions come from. So she writes very well.
There's another question.
This is a small conceptual question. So in the Poisson summation formula,
Yeah.
the right hand side is summed over a lattice lambda star. Where is that lattice different from lambda always? So the lattice
Lambda was a generic this thing, but E8 star is the same as E8. For E8, the dual lattice is the same.
in general it need not be the same.
No.
For
So in the Poisson summation formula, lambda star will come.
Any other questions? Comments? If not, Mahan, we can go to the second. Yeah. Mahesh.
Okay, great. Thanks for this. Yeah, great stuff. And so now we move to the other aspect of Viazovska's work. Mahesh will tell us. Thanks, Mahesh.
Mobile side. The center is pointing.
That's fine. Just confirm. Okay. May I?
Yes,
start?
yes, please.
Okay. Yeah. So, well, thanks for inviting me to talk here about Viazovska's work. So I'll not say how little I know because you'll realize this by the end of my talk anyway. Okay. So there will be a lot of repetition in my talk with Shobha Madan's talk. This is because I was very lazy and did not coordinate, and you can also see that I prepared these slides yesterday, so that's why the wrong date. Not before that. Okay. So let me define what a lattice is again. So it's just a discrete subgroup of Rd of rank D. Okay, so that's the lattice in D dimension. Another way of saying this is you just take the Z span of a basis of Rd. A lattice packing is simply at each lattice point you put a ball of radius R, and you take the biggest R that you can take. If you do this, and that's the minimum, half of the minimum of the lattice vector. Length of the non-zero lattice vector. So, okay, and then as Shobha explained, so sometimes it comes, yeah. Okay, the density is kind of whatever the volume of the sphere is, ball of radius r/2 is times the reciprocal of co-volume of lambda. Okay, so that's we have seen this. All right, so so here's an example of lattice. This is just Z2 in R2. Everyone knows. If you put sphere there of dimension 2, this is what you get. This is not the densest packing as we saw in the previous talk. But the lattice of interest is this one. Okay, so so you take all the so I'll construct E8 out of this, and I'll say a few words about this. So what you do is you take all coordinates you take elements of Rn with integer coordinates, but with an extra condition that they sum to an even integer. Okay, so it looks like this in 2 dimension. You skip every other point. Sorry, this, yeah, cool. Yeah, skip this, and so on. Skip something here, skip something here. Okay, from Z2. Why is this a lattice? So it's not hard to figure out why this is a lattice. For instance, you can just take this basis of our Rd, and then take the Z span of that, and that gives you D sub D. Okay, so all right. The minimum distance between lattice points in D sub D is square root of 2. So for instance, this one, right, in 2 dimension, and you can see that this also happens in higher dimension. Okay. All right. So so here's the 2-dimensional thing in D sub 2, and this is not the densest packing in 2 dimension, but this is how you would see projection of the densest packing from 3 dimension to 2 dimension. So maybe this picture is interesting, even though it's not the densest packing. And so there are all these holes right here, where somehow if we have 3-dimensional thing, then the top layer would fit into this perfectly. Okay. So yeah, so D3 gives the densest sphere packing. That's one way to yeah, that's one way to get the densest sphere packing. So this is due to Hale's set, and we heard the story in the previous talk. This is picture. This is the only picture I borrowed from the internet. So this is from Wikipedia, and it says this is how I should refer it to. So a load of old balls. Okay, so This is how it has to be attributed. So, all right. So D4 and D5, these give the known densest sphere packing in dimension 4 and dimension 5 respectively. I don't know whether it's conjectured that these are the densest or not, but these are the known densest sphere packing in dimension 4 and dimension 5. Okay. Beyond that, okay, sorry. So before going to that, okay, so the densest sphere packing in two-dimensional is this one. So this is the E2 lattice, and there is what is called the concept of so as we saw, this is kind of classical. Okay, so the complete proof was given in 1940. So we know that this is the densest sphere packing in two dimension, but there is a notion of what is called universal optimality, which I'm not going to say anything about, and that's not known in dimension 2. It's known in dimension 8 and dimension 24, but it's not known in dimension 2. Because in dimension 2, we don't know what how to construct these magic functions that Viazovska constructed. Okay, so even in 2 dimension, there's something to be done. And in a talk in her ICM talk in 2018, Viazovska said that this seems tractable and interesting, and somebody should do it. And it's not been done, and she has had many students, and it's not been done by her students. So I suppose it must be less tractable than what she thought 4 years ago. Okay, so it's not just an academic question of constructing kind of this magic function in dimension 2. It has an application for proving what is called universal optimality. All right, going back to the more general case of D sub D, beyond dimension 5, these certainly don't give you the densest packing, because there are too many holes in it. Okay, there are too many holes in D sub D. So hole is kind of a, you say that there is a hole at some point if that is the local maxima for distance from the lattice. Okay, so for instance, the point half, that will be a hole, and this hole is kind of size square root of D by 4 in dimension D. Okay, so when D is small, this hole is small, and you can't put any more spheres. That's why sort of things work in D3 and may work in D4 and D5. I don't know. But something interesting happens when D is equal to 8. This hole is exactly the size that you can fit another sphere of radius 1 by square root of 2. Okay, so which is what you would do, because you see the distance, the shortest distance in D sub 8 is square root of 2. So you would put balls of radius square root of 2 by 2, and so this is exactly kind of enough to put another ball there. Okay, so that gives you an idea of how to construct a packing using D sub D, and that's what gives you E8. Yeah, this one has to press really hard. Okay, so you take union of D8 and then a translate of D8 by this vector half. Okay, so again, why is this a lattice? Well, one, I mean, there are better ways of writing bases, and especially if you study representation theory and so on with thinking diagrams, there are better ways of writing a basis. But one easy way of writing a basis is just take this half vector and then E1 plus EJ for J between 1 and 7. So that gives a Z basis for E8. Okay, so that's the basis of R8, and its Z span will give you E8. So it is a lattice. Okay, and it if you just write this these vectors as columns, then you get an 8 by 8 matrix, which is so yeah, you put this one at the end, so you get an upper triangular matrix, and you see that its determinant is 1, and so that gives you that it's unimodular, right? Its co-volume is 1. It's unimodular and it's even, so square of length of any vector is an even integer, and it's integral. So and so what this means is that it's dual of itself, because E8 will be contained in its dual, and then the co-volume for the dual will also be 1. So you'll get that E8 is equal to E8 star. Okay, so all right, and then the packing radius of this is square root of 2 by 2, right? So 1 by square root of 2, because that comes from D8 itself. All right, so that's how you get E8 and the sphere packing on E8. All right, yes, and the density, as we saw in the previous talk, is pi to the 4 by 2 to the 4 times 4 factorial, which is this number, which is 0.2536 and so on. All right. Oops. Yeah. Okay. So as we saw in the previous talk, what we now need to show that this is the densest packing. Okay. So we want to show that this is the densest packing. So we want to get this number out of this linear programming bound, and so we want to construct this magic function, this even-Schwarz function from R8 to R, which satisfies all these properties with that R in the theorem equal to square root of 2. Okay, so because once we have that, the upper bound will be given by volume of ball of radius square root of 2 by 2. Okay, which is exactly the number on the previous slide. So R has to be square root of 2. Okay, and as we saw, it's enough to take F to be radial, right? And so, you know, as was mentioned in the previous talk, this linear programming bound, this paper appeared in 2003, and then they did in that paper itself, and after that they did lots of computations to kind of get to this R. And the way to do this is sort of the way they did this computations is by taking F to be polynomial times something. Okay, and then there are lots of clever ways of choosing these polynomials, and I know very little about these, but they kind of did this. And what seems to what this seems to give is in each of those dimensions up to 36, this you get better and better, sort of smaller and smaller R, but it seems to converge to something. So that line you saw in Shobha's talk, this upper bound, that is pretty close to what you can get optimally, right? So even if something better seems to happen in dimension 16 or dimension 4, it seems there's no hope of getting exact result using linear programming bound in those dimensions. Okay, so I don't think they expect to get solutions to sphere packing problem in any dimension other than 2, 4, and 24. Okay, and 1, of course. So that's, okay. So yeah, that's just a kind of a remark about how they did the numerical computations. And so this seems, you know, one could give several lectures just about this, but that's not our objective. My objective is to tell you something about construction of these magic functions. Okay, so modular forms. This is the upper half plane, as we know. So all complex numbers with imaginary part bigger than 0. And then SL2Z, this is just 2 by 2 matrices over Z with determinant 1. It acts on H by this Mobius transformation as usual. So ABCD acts on Z by AZ plus B divided by CZ plus D. And I'll need certain subgroups of SL2Z. So these congruence subgroups, or not many. So I'll just define this. So for an integer n, we'll only use this for n equal to 2 actually, and n equal to 1 is just SL2Z. So all the 2 by 2 matrices over integers with determinant 1, so that it's congruent to the identity matrix modulo n. Okay. All right. So those are our objects, so upper half plane and SL2Z. Okay. Now, if you have a function from the upper half plane to complex numbers, you can define what I'll call weight k action of SL2Z. Okay. So that's why this f sub k. And what is the weight k action? So the weight k action of A, B, C, D, it's a function which takes z to this particular thing. Okay, Cz plus D to the minus k, f of Az plus B divided by Cz plus D. Okay, so that's again in upper half plane because of, as I said in the previous slide, SL2Z acts on. Okay. So a weight k holomorphic modular form for SL2Z. Okay, so you would also need it for gamma n. So here for SL2Z, so these are what are called level 1 modular forms. So it's a holomorphic function from H to C which satisfies various conditions. So first of all, it's holomorphic, okay, from upper half plane to C. Secondly, the weight k action gives you back f of z itself for all gamma in SL2Z. So this is what makes it level 1. It happens for the full modular group. Okay, so for instance, in particular, it's so 1, 1, 0, 1 is an element of SL2Z, and the weight k action of 1, 1, 0, 1 on f gives you f of z plus 1. So the condition says that it should be equal to f of z, which means that it's periodic. Okay, and that leads us to our second condition, that f is holomorphic at the unique cusp that we have in level 1. So there's a unique cusp at infinity, and what that means is that you take the Fourier expansion given by the fact that it's periodic, and the Fourier expansion should begin with the 0th term. So there are no poles at infinity. Okay, that's what it means. Okay, and so if you drop the second condition and replace it by something weak, so something, so you allow some poles. So if there are finitely many terms on the negative side, then you get what are called weakly holomorphic modular forms, and those also come into construction. Sort of more, yeah, in dimension 8, but also in dimension 24. So, okay. So, these are modular forms. Now let's look at some example. Yeah, okay. Before looking at examples, what are gamma n modular forms? So weight k modular holomorphic modular forms for gamma n. So again, so these are called level n, if you like, or gamma n level, if you like. So this is holomorphic functions from H to C, which satisfy this, but now only for gamma in gamma n. It need not be for all gamma in SL2Z. That's one. So in particular, you may not have 1, 1, 0, 1, but you do have 1 n 0, 1. So you have a periodicity, with period n. And then you get a Fourier expansion like this. And again, you want it to be holomorphic at all cusps. So when n is bigger than 1, you may have more than one cusp. You will have more than one cusp. So one way to write this condition is to say that f sub k gamma is holomorphic at infinity for every gamma in SL2Z now. Okay. So that's not a typo. That's a, yeah, that's, so you kind of take all these finitely many translates that you would get with weight k, depending on sort of what SL2Z modulo gamma n is, and you want all of them to be holomorphic at infinity. So that's right, because the action of SL2Z on the cusps that will be transitive. So, all right. So, so these are modular forms of level gamma n. Okay, now we saw an equation of this form in the previous talk. And the fact is that SL2Z is generated as a group by these two elements, okay? T, which is just the translate, and then S, which is this 0, -1, 1, 0. And so every element can be written as some word in these T and S. And so if you want to check something is a modular form of full level, you simply have to check the invariance under T and invariance under S. So you have to check these two things, okay, to show that it's a modular form. Another kind of use of this is if you want to use a modular form, then maybe you know it's enough to kind of use these two things in some combination. So that's the kind of thing that Viazovska uses very cleverly in her construction. Okay, so it's kind of enough to use these two kinds of equations in some sense. Okay. All right. So yeah. So some examples of modular forms. Okay. So explicit examples of modular forms are very hard to write down, as you can imagine. One class of examples that you can write down are Eisenstein series. And so this is not true just for these modular forms, the most basic ones that we are using, elliptic modular forms, but also kind of more generally, writing down examples of modular forms are hard. So, so here are sort of the definition of Eisenstein series. So here k is bigger than or equal to 4 because we want this this sum to converge absolutely, and I'll say what happens when k is equal to 2. In any case, so this is the basic thing. You take sum over this lattice Z2, all the non-zero elements in the lattice of Cz plus d to the minus k. So that's basically what we want, and then you normalize it in some way. Okay, so you normalize it by dividing by multiplying by this factor 1 by 2 zeta k. So zeta k here is the Riemann zeta function. Okay, so again, because k is bigger than or equal to 4, this is kind of just the Naive-Dirichlet series that you take. The advantage of normalizing it this way is that the Fourier expansion is actually a rational number. So zeta of 1 minus k is a rational number. And because k is even, zeta of 1 minus k is a non-zero rational number. So this is it's legitimate to divide by this. And this sigma k minus 1, these are divisor sums. So these are just sum of all the divisors of n, sum over all the divisors, positive divisors of n of d to the k minus 1. So so some ranges over d which are divisors of n, and you're taking d to the k minus 1. Okay, so that's the yeah, that's the divisor sum. Maybe I'll just write it here. So sigma k minus 1 of n is summation d divides n, d greater than 0, d to the k minus 1. Okay. All so that's a nice Fourier expansion for E sub k, the Eisenstein series. Okay. So I told you that writing down modular forms explicitly is very hard, but for SL2Z, a nice result is that so if you take modular form of weight k and a modular form of weight L, then its product is a modular form of weight k plus L. This you can just look at the definition and verify that the product will satisfy all this property, and it will be of weight k plus L. So the ring of you take all modular forms, you know, of all weights over SL2Z, it forms a graded ring, and you can show that it's generated by E4 and E6. Okay, so there's some very nice structure to the graded ring of all modular forms. And this is the kind of thing that allows you to, so first of all, it tells you that the space of modular forms of any weight is only finite dimensional, because you just write down all the monomials in e to the you just write down all the monomials in E4 and E6 of a particular weight, and you can write any modular form as a linear combination of that. So it's finite dimensional. And this is the kind of thing, the finite dimensionality is what allows you to prove algebraic results, or work with modular forms and prove exact equations, because you can work with finitely many terms and get some results, finitely many terms in the Fourier expansion, if you want to show that two things are equal and so on. Okay. Yeah, so this finite dimensionality is what kind of relates these analytically defined objects to arithmetic or sort of to number theory. Okay, so here's another example of a modular form, and this is related to E8. We are not going to use it in any direct way, but it's still an interesting example, and it illustrates this point I was making about using finite dimensionality. Okay, so so theta E8, this is the theta series attached to this lattice, so you can attach it to any lattice. Is just you take this this thing. Okay, so it's counting. So if you write it as e to the power pi I nz or 2 pi I nz, it's just counting the coefficient will count the number of lattice number of points in E8 with length 2n. So that's what it will count. So this is some kind of generating function, and you can show that this is a modular form. And again, to show that this is a modular form, you use Poisson summation formula and the fact that E8 is its own dual. So this can be, you can take that as an exercise if you have not seen and want to apply the theorem that was mentioned in the previous talk. Okay. So you can show that this is a modular form of weight 4, and it's first it's holomorphic, and so it's first the 0th Fourier coefficient A0 is 1, and there's only one dimension. The space of modular forms of weight 4 and level 1 is one dimensional, so it has to be equal to E4, right? Just because the first coefficients match up. So so this is just E4, and so that's how you can show this equality. So in particular, you get a nice formula for the number of elements of this is an unfortunate thing that E8 is also an Eisenstein series and E8 is also this lattice, but they are both very standard notations, so can't do anything. So it gives you a very nice formula in terms of these divisor sums for the number of vectors in E8 of length 2n. Okay, so this is how you kind of prove something using this finite dimensionality. Okay, now coming to what happens in weight 2, and the reason so of course this is an interesting example, but another reason why I'm mentioning this is we are going to use this later. Okay, so if you just write down this expression, this first thing for E2, then that sum does not converge absolutely, and so it's kind of not very useful to define E2 that way. But this particular thing makes good sense. Okay, the Fourier expansion makes sense. So you could just define E2 to be something like this. Okay, zeta of -1 is -1/12. Euler knew this. Ramanujan found this by himself again. So zeta of -1 is -1/12. And so that's why you have -24 here. So this expression is basically just writing this for E2, and that makes sense, but it's not a modular form. Okay, if you do E2 minus 1 by Z, you don't get E2 and scale it by Z to the minus 2, you don't get E2Z. You get this extra factor. Okay, and so these are what are called quasi-modular forms, and I'm not going to define them. But anyway, this, if you like, this is a quasi-modular form, right? So this is the only example that, anyway, I know, and so this is the only thing that we are going to use. All right, so and of course, when Viazovska uses this factor is important, right? So it's good that it's there. Okay, another example which you can write down explicitly. So this is Ramanujan's delta function, which is defined as a Q expansion this way. Okay, so Q is e to the power 2 pi I. Q is e to the power 2 pi I. Maybe I should have said this somewhere on the previous slide, but Q is e to the power 2 pi I. And so the Q expansion is this explicitly, but it also is equal to e to the 4z cubed minus e6 square divided by 728. So again, this is just to normalize things so that you get this kind of thing. And this is what is called a cusp form. It's a cusp form because the 0th Fourier coefficient vanishes. Okay, so this begins with Q and then Q squared and so on. Okay, so this is a cusp form, and it's a unique cusp form of weight 12 of full level. So and this is again, one of the few examples of cusp form that we can write down. So we can write down Eisenstein series, we can write down theta series, and then we can write down this delta. Essentially, those are pretty much everything we can write down. Okay, so this vanishes at cusp, but not at any other point, right? Just by this looking at product, you can believe me that it does not vanish at any point in the upper half plane. Okay, so this is an example. I'm going to write down three more things as examples, and we are going to use all these. Okay, so these are the examples that we are going to use. So this is, if you like, this is sorry. Yeah, I looked for typos and I looked for this. This should just be there shouldn't be this n. Okay, so pi I n z. Sorry, this exponent n here is wrong. Okay. So so if you like, this is the theta series for the lattice Z in R. Okay, so it's a theta series. It's of weight half. Okay, but we don't want to work with those kind of things. So we take fourth power, and so this gives you a modular form of weight 2, and its level is gamma 2. Okay, it's not full level. And then you use so if you do the weight 2 action on U, you don't get U back, so you get something else which we call W, and then V is just U minus W. So these two, they should be W of Z. So these two things are again something we are going to use. So up to now, everything kind of what I said is a holomorphic modular form, but eventually we are going to construct weakly holomorphic modular forms out of these things. Okay, all right. So so that's the sort of crash course on modular forms with all the examples and everything. Now we are going to go to construction of magic functions. Okay, and so it's what I'm going to do is I'm not going to tell you how to construct this magic function required for dimension 8, but I'm going to give you construction of another function which has no application in sphere packing or anything else. I know it's just to tell you how to control behavior at certain discrete set of points. Okay, so square root of n. This is the thing that appeared in the last theorem that Shobha mentioned about controlling behavior of square root of n. And so it's that theorem is sort of, I mean, as a theorem, of course, it's amazing, but I think Viazovska also conjectured that thing in her original paper. So that was very insightful, in my opinion, that such a thing should be true. And the proof is using modular forms. There's kind of, there are some, since then people have proved things about sort of reconstructing a Schwartz function from its values at a discrete set of points in a purely analytic way. And there you can drop finitely many points and you can still construct a function, but in her theorem you cannot. So this has really some kind of arithmetic flavor, and that's why I think the square root of n play a role. But yeah, so I don't think there's any analytic reason for that. Anyway, so this is just repeating what was said in the previous talk. I want to construct f, and it's useful to break it up into eigenfunctions for the Fourier transform. Okay, so eigenfunction with eigenvalue 1 and eigenfunction with eigenvalue -1. Okay, so what do we want? We want radial eigenfunctions for Fourier transform, f plus and f minus. So that it has a single root. I mean, they both have single root at root of order 1 at square root of 2, and double roots at square root of 2n for all integers n bigger than or equal to 2. So of course, I mean, when I say we want this, I mean that it's enough to construct something like this. Okay, you could have, I don't know, a priori you could have even order roots at square root of 2n when n is bigger than or equal to 2, and odd order root at square root of 2. But yeah, so I don't know, like, a priori how you rule that out for magic functions. Anyway, all right. So what, as I said, to illustrate the method, what I'll do is I'll construct a Fourier eigenfunction g, let's say with Fourier eigenvalue -1, and simple roots at square root of n with n bigger than or equal to 3. Okay, so so it will take non-zero values at 0, 1, and square root of 2, but for square root of 3, square root of 4, and so on, it will have simple root at each of those points. Okay, and this is going kind of in somewhat other direction. I mean, than what was suggested in the previous one. This integral down with this sign factor and then proving it. So we are going to go in the reverse direction, and I'll sort of say what I mean at the end. Okay, so this is, I think, Viazovska's kind of one of the insights, that if you take something like this, then you can control behavior of you can construct some g with control on the roots. So what you do is you take this contour integral from -1 to 1 of some holomorphic function on the upper half plane, and the contour is just the the semicircle from -1 to 1 with center at 0. So you want to construct this psi so that you get required properties of G. Okay. Now, how do you kind of construct roots of? How do you find out values of G at square root of n? Let's assume some sort of periodicity for psi. Okay. And again, I mean, at each step in her proof, it's kind of, everything is so non-canonical that it's really impressive that one can figure out all those things. It's not like you write something down, you have one idea and then you follow your nose. It's certainly not like that. And okay, so you say, okay, if this is periodic, but it's not one periodic, right? So that doesn't seem to work. So if it's two periodic, then this will have Fourier. Yeah, this will have Fourier expansion like this. So this is 2 pi I nz by 2, right? So an summation e to the power 2 pi I nz by 2. So pi I nz. And assuming that, you know, our functions are nice, our functions are Schwartz functions, so you can interchange integral and summation, and you know, I'm an algebraist anyway, so I don't mind these sort of things. So yeah, so you can then figure out what the value of g square root of n at g at square root of n is, and that's just the minus nth Fourier coefficient of psi. Okay, so if you want this g square root of n to vanish for n bigger than or equal to 3, then you better have this thing, you know, start with -2, -1, 0, and so on, this summation. Okay, now of course you can ask, why can't you have vanishing at all square root of n's for all non-negative integers n, and yeah, I don't know why that doesn't work, or if it works. Okay, so you know, my ignorance about the subject, I did not try to do that. All right, so with this periodicity you can control what happens at square root of n. So that's one part. The other part was g was an eigenfunction for the Fourier transform with eigenvalue -1, and so here's a Fourier transform that you can try to calculate. So Fourier transform of this function is this. And so again, assuming that you can interchange the Fourier transform and this contour integral, you get that g hat of y is this. Okay, so again, I'm using the fact that g is a Schwartz function, or a nice function. Okay, and so if we want g hat to be minus g, psi must satisfy this functional equation now. Okay, so this is just something you try to figure out. So what does this mean? This means that psi is a weakly holomorphic modular form, because you see it has to start from -2, is a weakly holomorphic modular form of weight -2 and level gamma, which is this subgroup of SL2Z generated by S and T square. So of course I did not define modular forms of level gamma for such a subgroup gamma, but this gamma contains gamma 2. So it's somewhere between gamma 2 and SL2Z. Okay, gamma 2 and gamma 1. So so we are eventually just going to use gamma 2 in a way, but anyway, this is a weakly. So we want to construct a weakly holomorphic modular form of weight -2 and level gamma. And so what we are going to do is, again, you know, it's not clear to me why this should work, but what we are going to do is we are going to construct a holomorphic modular form delta times psi. So we are just going to multiply our psi by delta. So you get a weight 10 modular form. And now it's not weakly holomorphic anymore. It should be holomorphic because yeah, so you know, that's why I said here it suffices to construct a holomorphic modular form of weight 10, which is of this form. So what I mean is I'll construct something of weight 10 on gamma, which is holomorphic, and I'll just divide it by delta. So that's what I mean by this sentence. Okay, so it suffices to construct something of weight 10 on gamma, which is holomorphic, and then I'm going to divide it by delta, and I'll take my psi to be that. Okay, so this is what I'm going to do on the next page. So remember, we had these u, w, and v on one of the slide. So u was this weight half theta series given by the lattice z inside R, and you take its fourth power. So that was my u, and then w was just a translate of that under t. And so I'm going to make it even more mysterious than what it is in Viazovska's paper, because she tells you how to reach this point by saying you have to okay, let me make a few remarks. So you want a holomorphic modular form of weight 10 on this gamma, but gamma 2 is contained in gamma. So you want a holomorphic modular form of weight 10 on gamma 2. Now any modular form on gamma 2 is so as a graded ring, the space of modular forms on gamma 2 is generated by U and W. I think I may have said this at some point. Oops, I think I forgot to say this. So as a graded ring, the gamma 2 modular forms is generated by U and V. So if you want a weight 10 modular form, a holomorphic modular form on of level gamma 2, then you can write it as a linear combination of U to the 5, U to the 4 times W, U to the 3 times W squared, and so on. Okay, all weight 10 monomials in U and W. And then there's a kind of systematic way of doing this so that you arrive at something like this. Okay, so I'm not going to really say how you arrive at this, but this is the weight. The numerator is the weight 10 holomorphic modular form of level gamma 2 that you take, and then you divide it out by delta, which is a weight 12 holomorphic modular form. And this makes sense because delta has no root in the upper half plane. So this psi is still holomorphic in the upper half plane. Okay, and you can work out what the Fourier expansion of this is, and you get that the 0th term is minus 240, the minus 1th term is 8, and the minus 2th term is, so a sub minus 2 is 1, and then a sub minus 3, minus 4, and so on. Those are all zeros. Okay, so so this kind of all works. Okay, but now this expression is kind of very hard to do for double roots. Okay, how do you get double root out of such a thing? It's not clear. And so what she does is she says, okay, you can rewrite this G in this form, and this looks much closer to what we saw in Shobha's talk, right? This expression. So by breaking up this contour integral from -1 to 1 into an integral from -1 to I, and then 1 to I, and then making some shifts and change of variables and whatnot, kind of people who are very good at this, they do it, and then eventually you end up with something like this. Now this integral, so this has lots of kind of zeros at square root of n's, and then this integral makes sense only for x large enough. Okay, and so it has poles when mod of x is small, and that's what Shobha was saying, that if you want to cancel zeros of this at unwanted points, you need this integral to have poles. And the way to do this is kind of you start with this expression and then you go back to an expression like this. Okay, and using this you show that poles and zeros are cancelled. Okay, so actually what you do is you in the way the proof is presented, you kind of start with some expression like this and then you go backwards and use this. Okay, so I hope that kind of makes some sense. But the good thing about this is that you can do this even for double roots. So this last expression is what generalizes, generalizes in the sense that if you had asked me to do it, I wouldn't be able to do it, but Viazovska did it. So the minus thing is she defines it like this. Okay, so yeah, I mean, it was the expression was slightly different in the previous talk, I think, but yeah, this is the expression, and then you take psi to be something like this. Okay, again, the way to guess what this psi is, you start with this expression, you kind of go backwards to what we did for G, and you end up with some somewhere you can calculate the zeros using Fourier expansion, and you figure out what all the properties your psi needs, and then you write it like this. Okay, so this has let's see, so U has weight 2, so this is 4, and then yeah, so this is again weight -2, right? So psi still has weight -2 because the numerator has weight 10 and the denominator has weight 12. So so this kind of works. So you can show that it has the correct roots and to the correct order, and it is an eigenfunction with eigenfunction for Fourier transform with eigenvalue -1. Okay, so that's those are the two things you can show just by doing what we did for G, and then for plus it's actually even harder. So so what you do for minus, by just doing the same thing, it doesn't work for plus. Yeah. So because there are some minus signs that come out when you do Fourier transform, right? So that's why it kind of doesn't work for plus. So, but again, so this expression I'll not write as 0 to infinity, but as 0 to I infinity, because then it's easier to describe what this function chi is. And the function chi is in terms of this quasi-modular form. Okay, so you can't, it seems you can't use modular forms anymore. You have to use quasi-modular forms for plus 1. So, so again, you can control roots and the order of those roots using this this thing that we did for G, and you can show that it's a eigenfunction with eigenvalue +1. And from okay, now that we have f minus and f plus, you can construct your f. You still have to show the inequalities that that it's that f is negative beyond mod of x equal to square root of 2, and you have to show that Fourier transform of f is positive on the entire 0 to infinity line. And so that's more work, and I'm not going to show you how to do that. But those inequalities actually come by taking these linear combinations of psi and chi, and those inequalities are satisfied by, for these things itself. And so when you do the integral, you get inequalities out of them. Yeah. So this is for dimension 8, and dimension 24 is kind of even more complicated. But as you saw in the previous talk, this paper appeared on 14th of March, and then the next paper appeared on 21st of March. So clearly people who had thought about it a lot knew where to look and what to do. So that's dimension 20. So I'm not going to say anything about that. Yeah, and as I said, all this is kind of so non-canonical that we don't know how to do this kind of thing in dimension 2. So we don't have a magic function in dimension 2, even though it's expected to exist. Okay, I'll stop.
Okay, for some of us, thank God English exists. Okay, so we'll understand some of it. So, okay, so questions? Yes, over there. Yeah, so I had the following question. So what do we know about so I understand most of this techniques are specific to dimension 8 and 24, but what do we know about density of sphere packing as dimension d goes to infinity? Is there some asymptotics or anything? Because I mean, for example, law of large numbers will tell you that spheres will look like cubes in high dimensions, right? So we expect something.
Yeah, but I don't think, I mean, this yeah, so I think what is known is that maybe this linear bound or whatever known upper bounds deviate from the expected thing by exponential. So that curve, those curves you saw kind of going apart very quickly, this is what happens. But apart from that, I don't think, each dimension seems to have its own peculiarity. So I don't, yeah, even as asymptotics, I'm not sure. I recently met a student of Viazovska who's doing some numerics to figure out if the asymptotics make any sense, but this is very far from what I do usually, so I don't know.
Thanks.
That's what Balaka is referring to is something, I mean, he sort of probably has Larry Good's work in mind like that, right? Paulo Levy's isoparometric inequality. So that's a different ballgame. I don't think these are the relevant things.
Questions? comments? Yeah.
So for non-mathematicians, can you say anything a little bit about those two bounds? Because they looked much simpler as curves, the exact results. The lower bounds and the
Yeah, the actual known things is kind of very zigzag, right? So it
yeah.
of
But,
seems to no. So the lower bound, as Shobha Madan was explaining, is just a kind of a simple-minded thing. What you do is you take a sphere packing, and then so that you can't put any more sphere of that radius. And if you double the radius, you should cover the whole space. So that gives you something like 2 to the minus n as the lower bound. And there are, I think, results known better than that, but maybe not too much better than that. So that's, and the upper bound is this linear programming bound, which again so this is not kind of an asymptotic thing, because in each dimension you would have to construct at least some function which may not be an optimal one. So the R in that linear this theorem mentioned by Shobha in the previous talk is it may not be an optimal thing, but in each thing you have to construct some function with a specific R, and that will give you an upper bound. And I think what these people have done is computations up to dimension 36. Yeah, there are, I think, some asymptotic bounds known which work for any dimension, and that lies strictly above this curve, at least in the up to dimension 36.
Okay. Yes, man. Yeah, go ahead.
Yeah, so I have a quick question. So you mentioned universal optimality for dimension 2.
Yes.
And you said that you are not going to talk about it.
Because I don't know anything about it.
But there is something you're saying is I mean, what exactly would be the expected output in dimension 2 of a magic formula?
No, whatever this of the magic formula, I don't know. I mean, yeah, that's should again, I mean, it should again be the magic function with R equal to, it's 1, I think, that gives you that you apply in the linear programming bound. So that's the magic function. Yeah, but what it will give you is that A2 is the optimal, universally optimal lattice in dimension 2.
But that's something we already know.
No, that we know it optimality only for sphere packing. This universal optimality is more general. So for that we don't know in dimension 2, so far as I understand. So in dimension 8 and 24, actually that's known. So the more is known in dimension 8 and 24 than in dimension 2.
Okay. So the other thing is that, see, at some place you were looking at not the principal formula. I mean, you are not looking at gamma 2. You are looking at something that was an overgroup of that. Gamma,
yes,
right?
yes.
So does her proof use the
yes,
full group?
Yes, it uses gamma to kind of guess what these things would be. Yeah.
It uses all of gamma.
All of gamma, yes.
Nice.
Yes.
Okay. The other thing is that you mentioned somewhere this quasi-modular thing with this 1 by z.
Yes. Yes.
So that when you mentioned that it's somehow used in
in the construction of the plus eigenfunction. This E2 is the one that's quasi-modular.
Okay.
Yeah.
Okay.
It's not a modular form. It's only a quasi-modular.
Oh, thank you.
Are there any other questions? If not, then let's thank both the speakers for wonderful talks. And I would like all of you to actually have some snacks with us in the West Canteen. We have arranged some snacks, and